Okay, folks, again. So we have our first of two bigger presentations done by Duncan. Probably everyone knows him. So, Duncan, take it away.
Thank you very much. Yes, nice to see so many people here. Can everybody hear me okay and see the screen okay? I realise it's a very big room and I'm talking to sort of both ends. I want to make this a kind of interactive. I want questions all the way through. So if you're in the far corners of the room, you're welcome to either shout really loudly to interrupt me with a question, or come closer to the middle, whichever you prefer. So, right, this talk is about binary serialization, but it's really about optimization. So it's supposed to be a case study. Right? I'm not just trying to tell you how awesome this new library is, although it is awesome. But it's supposed to be about optimization techniques that are hopefully transferable to other libraries, other places, hopefully. But because it's a case study, necessarily I have to go into some of the details about what this library does. You can't just present these sorts of things in the abstract, it just doesn't work. So I will have to start with a bunch of stuff about what is all this binary serialization that we're doing, so you'll understand what the code is looking like, and how we're trying to optimize things. So, just quick introduction to the particular approach to binary serialization that we're taking, and what we mean by binary serialization here. So when you're dealing with binary data, there's really sort of two major use cases. One is you are dealing with some externally defined binary format. You need to parse X509 certificates or something. And the other is, I have some data in Haskell and I want to serialize it, send it over the network, or dump it to a disk and return it later. We're dealing in this library with the latter case, serializing stuff, not with the parsing externally defined formats. Okay. Now, unfortunately, the binary serial packages do both, which is rather confusing, which is the fault of myself and Don Stewart when we first started. We didn't realize that was the important distinction, but now we do. Anyway, so this new library, the short-term goal is to implement the serialization sort of layer, or redo the serialization layer of binary library. Ultimately, I'd like to integrate it, and the other co-conspirators, maintainers of the binary library, are mostly on board with this idea. The main thing is it's got much better serialization format, but the thing I'll be concentrating on in this talk is the performance. And it is a lot faster, which is nice. Everybody likes faster binary serialization. So briefly, the format is CBOR. It is recently defined RFC. You can think of it, if you've not come across it before, you can think of it as JSON but in binary, a compact binary encoding of a JSON-like data model. If you've come across message pack, it's very much like that, just slightly better designed, hindsight. It's much more compact than the existing binary and serial formats, which were terribly designed by, again, myself and Don. And it's well suited to Haskell's tree-like data structures. So it's a reasonable choice. If you want to dispute that with me, come talk to me later. That's not the point of this talk. We're going to take it for read, this is a reasonable thing to do, and see how fast we can make it. So just to start off with, these are the sorts of examples. This is what CBOR values look like, at least in their textual diagnostic notation. And they look much like JSON. There are some slight differences with JSON, but it's not a big deal. So in particular, we have lists and maps, and that's what gives us trees, right? That's what we use to encode any kind of structure. And they're heterogeneous, of course, just like in JSON. So we're going to encode Haskell, arbitrary user-defined Haskell types with this sort of encoding. We're going to, each constructor will be encoded as a CBOR list, and when we have multiple constructors, the tag, we will use a tag, an integer, to say which constructor it is. Fairly simple. This is actually quite nice because it allows you to do versioning, because you can increase the tag numbers. But that's for a different talk. So hopefully fairly clear, constructor examples on the left and how we're going to encode them on the right. Yep, question here?
What if we dumped it into CBOR and then changed the order of the constructors?
The tag numbers have to match up. That's what we're relying on here. Yeah? Oh, yeah, sorry. So the question was, what if we dump the CBOR out to disk and then go and change the numbers and then try and bring it back in again, yeah, it's going to fail. Where this particular way of translating Haskell constructors to CBOR is relying on the tag numbers.
But it will fare nicely, right? So it will fare with an error.
Yeah, yeah. It would, in this case, if it was a number that was used somewhere else, it would say, well, it's the wrong length, or one of the fields doesn't match.
But if they match, but if the fields match, so if it's two strings field, but one of them says send the nukes, the other says send the present, then
in that case, yeah.
So there is no versioning. So there is no versioning.
Oh, there is versioning, but it relies on the tags being used in a systematic way. You could also do these things with names and maps, object style. But this is the encoding that I'm using for now. Okay. So conceptually, a CBOR value, it's like a JSON tree-like value, conceptually, when it's serialized, it's represented as a sequence of tokens, and those tokens have a binary representation, and so that is the overall binary representation of the flattened CBOR value. So, for example, here's a list 1, 2, 3. As tokens, that's list of length 3, followed by integer 1, integer 2, integer 3. Those are the tokens, and then each of those tokens has a binary encoding, and then the overall encoding is just a concatenation of all that. So that's what gives us the structure. So the strategy we're taking for serializing and deserializing is that we're never going to build an intermediate CBOR value, like a generic CBOR value as a ordinary Haskell algebraic data type. We're going to go straight from a Haskell value to CBOR tokens, and straight out to binary, and then straight from tokens into a Haskell value without any intermediate representation. So the sort of instances that we write will be in terms of these flattened, converting to and from flattened sequences of CBOR tokens. And then we'll use a binary parser and printer to specialize to working with those tokens. So this is in contrast to a library like ASON for JSON parsing, where it always uses this intermediate value type. The value type in the ASON library is the ordinary way in Haskell that you would represent a generic JSON term. And with ASON, you convert your Haskell type into a value, and then value goes out to string, and vice versa. It comes back into a value, and you convert from value back into your own Haskell type. And there's good reasons that ASON does it that way. It makes it, JSON, you have to deal with the problem that fields can appear in any order, and there are good reasons why it does that, but it has significant costs to have this intermediate structure. So ASON is a good example of this. Not that I'm picking on it, but it's, as I said, there's very good reasons why it does it, but there are big costs to it. So in particular with ASON, the intermediate structure is often larger because it's represented in a generic way. Everything is tagged, basically. So it's often larger than the final structure. Again, with ASON, it's necessary to build the entire, when you're deserializing, it's necessary to build the entire value, JSON value, before converting into your Haskell type. So you get this big memory spike. And the cost of allocating all that, and the fact that it's resident in memory, is just a big cost. So a real-life example that we had in a project we were doing, the IDE backend, which is the thing that sits behind the FP Complete Haskell Center, that has to talk to an external GHC process, and it sends big trees back and forth. And we were using initially ASON, sending JSON values over pipes, and the memory use was these enormous spikes. And we switched that to binary, and it went away. And that's not because it was binary. It's not because it was linearly faster or linearly using less memory. It's because, well, I suppose really, no, it is linearly less memory. Instead of deserializing into its intermediate structure, it goes straight to the final structure. So there isn't this big spike. So that's like the first transferable lesson is, if you can avoid it, don't use an intermediate structure, particularly if it has to be, if the way you would do it would be to allocate it all at once. That has big costs. So here's a slightly more concrete example, getting closer to what the sort of code that we would use for these instances would look like. For serializing, we're using a monoid. We have a bunch of functions which give us these tokens, list length, word, integer, string, etc., and we just append them, and that's the result. And so we do that for each constructor. So if you see the example at the top again, constructor 1 has 2 integers, so we're going to encode it as a list of length 3 with a tag of 0 and then the 2 body parts. And then similarly for deserializing, we're going to inspect the length of the list, then look at its tag, case analyze on the tag, depending on which tag we got, then we expect further the body parts. And we assert that the length is right. So that's the kind of thing we're going to expect to see. And that looks fairly straightforward. It's a monoid for serializing and a monad for deserializing, which is, if you've ever used the binary library, totally standard. That's how the binary serial have a monoid for serializing and a monad for deserializing. Okay, let's look at serializing performance first of all, because it's a bit easier and a bit simpler. Serializing is a lot easier than deserializing. So binary and serial are the existing established practice in this area. They are both continuation based, both for the builder monoid and for the parser monad. They're both what we call shallow embeddings. They are directly functions that, all of the combinators it provides are directly functions that manipulate buffers and pointers and offsets and things. And both of these libraries are actually extremely similar to each other these days. There's almost no difference. Sometimes one is faster than the other, but they're using exactly the same strategy these days, and they have exactly the same binary format as well. They probably ought to just be merged. So with both packages, they do really well on micro benchmarks, and they do quite badly on large-scale, real-world, lots of complicated structures, records, lists, the kind of thing that you run into in real applications. They tend to do rather badly. In fact, for encoding, they're only slightly faster than ASON, and I'll show you some more graphs in a minute, which are frankly rather embarrassing, especially as an author of one of these packages. So here's what the builder monoid looks like in binary, in binary package, and I think the serial one is essentially identical. It's continuation based, and it is sort of state on top of continuation. There's a buffer that's being passed around, and these functions work in I/O, and they just directly write bytes into this buffer, and then they call the continuation to do the next thing. So it's always passing these buffers around, and the buffers contain a foreign pointer and a bunch of offsets to describe what's going on with the buffer. So, as I said, we say they're slow. Why are they slow? It's very hard to give a really good answer for. I mean, if you come and talk to other of the binary library authors, they'll give you all sorts of different guesses, but we don't have a really good explanation. What we can say is it generates a great deal of code, these builder monoids, and essentially what you're doing is writing a code generator when you do this. You're writing these combinators which at some use site get inlined and then have to be combined and have to produce sort of perfect code at the use site. And what you're really doing is you're kind of programming the GHC inliner, or you have to deal with the fact that the inliner is doing things to your program, and you rely on it to achieve the code that you want to achieve. There's all kinds of problems with continuations. There has to be buffer checks, and then in the resume side of the buffer check, the code gets duplicated to do the same thing again. There's lots of buffers being allocated, lots of other constructors being allocated, but I don't have a really solid answer as to this one thing is what makes it so slow. And partly the reason that's hard to do is because on micro benchmarks it looks great. If you go and look at the core for some of these micro benchmarks, at least the ones that are not obviously totally flawed. So this is just showing how, in particular, the binary library varies wildly depending on the GHC version. The serial authors have clearly been better at, when new GHC versions come out, going and checking and tweaking things. So I don't think it's because serial is just more robust. I think it's because they've put more effort into tweaking. But if you go and look at the cases, like, for example, look at the decoding of the binary case in 784. That's the one that's running fastest there. If you go and look at that, you'll see that it has really very good code. And if you look at the ones where it's doing badly, there's something obviously going wrong with generics and inlining or something. And you could tweak that and it would make it as fast as it was in the best case. But this doesn't really tell you anything, because this doesn't tell us why it's going badly in the large-scale cases, because here it's not. Here it works really not well. This is another benchmark of a much, much bigger. This is actually deserializing 100 cabal files. Cabal structures are big and complicated. It's a reasonably good example of the kind of very listy tree structure that you get without any. There's no arrays in there. There's no dents, anything. It's all just pointers and pointers and pointers. So on these big benchmarks, we claim that the code is bad, but it's hard to pin down why it's bad because there's just so much code. You can't really figure out which bit and why it's wrong. Because and when you narrow it down to small benchmarks, it suddenly looks good again. So we haven't pinned down a precise culprit, apart from the fact that it's really hard to write these kind of code generator two-level programs. Okay. So as I accidentally skipped forward a slide. Simon Mayer is here, who's totally crazy. I think at this hackathon 2 years ago, well, maybe you had the crazy idea earlier than that. Had this crazy idea to a radically different approach to the serialization problem, which was to use a deep embedding. A description of these token sequences, and then do a separate sort of interpreter step that turns the sequence of tokens into the final binary data. So the instances that you write in that case would provide these constructors describing the token sequences, and then the interpreter just whips through those and writes stuff out into a buffer. Now this is a crazy idea, which you wouldn't expect to work, because it introduces an intermediate structure which has to be allocated. So it seems like this shouldn't make things faster, it seems like it ought to make it worse. But actually it makes it about 5 times faster, which shocked us and confused us and embarrassed us. Yes, here's the benchmark. So here's an encoding shootout. This is, again, a large-scale sort of real-world example. We're serializing, I think, 100 cabal files when they're fully in their in-memory representation, which, as I said, is just pointers galore. So the embarrassing thing here is that read show, right, is faster than ASIN, binary, and serial, right? Which is just using strings, linked lists of characters. So if we'd known this before, we would have been more embarrassed before. So the new code, this crazy idea that Simon had, is 5 times faster than show and 6 times faster than serial, which is quite shocking, really. So let me show you how that works. So we have an explicit. This is the deep embedding of the token stream. So tokens can be a word with the actual word followed by more tokens. It's just a list, but we're specializing it to the kinds of tokens that we can have. And then the encoding is just a new type. It's just a standard D-list, difference list, or endo-monoid, take your pick. And it's a monoid that combines by sort of continuation style. And then encoding a single word just wraps one in the other, passing the tail onto the next thing. Anyway, so now we can write down these instances in a fairly standard way. Each of these functions just turns into this encoding, and the generated code here is now really, really simple because it's just allocating a bunch of constructors. So there's really nothing to do. Yeah, question over here. That was a yawn, not a question. Okay.
I have a question.
You got a question.
Do you gain anything by not using a list here?
You mean why tokens rather than? It just eliminates one indirection, 2 indirections. One for the word is unboxed straight into the constructor, and we don't have to have an extra indirection for the list element. It's just directly in the tail. It's probably measurable. You might as well. So then you have to write an interpreter for this thing. So although the compiled side, the generated code with all those constructors is really simple, we can go to town on the interpreter and we can go as low level as we feel like. And in this case, we are using the kind of lowest level of the byte string builder monoid. And this works really nicely, and you can look at the core and go through sort of the standard iterations and look at the core and benchmark it and fiddle and then you can make the interpreter really, really fast. And so that's why this runs well. You have to optimize it to make it run fast, but it's still not entirely clear why this approach is so much faster. You have to really understand why the other approach was so slow, I think. So, okay, stepping back a little, what can we learn from this? What are we doing? So the sort of traditional, I'll call it the compiler approach to performance, is that you write your combinators using a shallow embedding, meaning directly manipulating functions, directly manipulating the stuff at hand. The combinators, because you're doing modular, combinatory style, combining things style approach, then obviously those components have to be defined separately, which means that at a particular use site they have to be combined and then fused, inlined, optimized, whatever needs to happen at the use site to get the good code that you want. And you're trying to achieve some kind of there's some kind of assembly that you're trying to achieve, or some kind of low-level CMM or STG that you're trying to achieve, and you're trying to achieve this sort of near perfect code by fiddling with the definitions and inline rules of these combinators, and relying on GHC to inline things exactly right and do everything exactly right. And that's you are doing two-stage programming. It's partly that you're writing normal low-level runtime code, but you're also having to think all the time about how does the rules work and the inlining and the unfolding and the optimizations. So it is a kind of it's almost like a compiler. You are doing staged programming in a sense, but you don't have as much control as if you were writing a compiler directly. If you're writing a compiler code generator, you can do what you like. Here you have to work with the kind of inlining rule engine, rewriting system, term rewriting that GHC does. So okay, the alternative here is this interpreter style, and you have to pay up front this cost of allocating this intermediate data structure. But then after paying that cost, there's a lot of other things you can do. You can try and now move as much work as possible from the kind of compiled side, the instances. You can try and move as much work onto the interpreter as possible, and then optimize the interpreter as hard as you can. So the approach there is your combinators use a deep embedding, i.e. they are data constructors or unfold to data constructors, and they just provide some description of the thing. And there's almost nothing to optimize at the use sites when you do that, which is really nice. And so then your interpreter, or multiple interpreters, of course, once you've got a deep embedding, you can do that. Your interpreter is now a single chunk of code, and a single chunk of code is a lot easier to optimize than this style where you have to, if you're looking at the core to see what's, if it looks okay, when you're doing the compiler style, you have to look at a specific example, and you have to look at n examples, whereas when you're writing an interpreter, you only have to look at one piece of code, the interpreter. So in some ways, it's a lot easier. So you've got and you've also got a bigger sort of code complexity budget. When you're inlining everything at the use sites, you have to be quite careful to keep things simple, because that's all you can manage, given the complexities of making it all work out right. Whereas when you're writing a single chunk of code, the interpreter, that doesn't, it's not polymorphic, it's much simpler. You can go to town on tricks and low-level optimization tricks and clever data structures and things that you would not dare to do at inlining at all the call sites. And also you can use more code, because there's one interpreter, rather than everything being unfolded at every call site or use site. Okay, so I've talked about encoding, or serialization. We move on to the slightly harder topic of deserialization. And can we apply the same trick to deserialization? It does look a bit harder. Printers are easier than parsers. So we would require some kind of description of the binary token parser.
I have a question.
Yes, question.
I don't grasp the difference between shallow encoding and shallow embedding.
Shallow embedding and deep embedding. What's the difference?
Yes.
Yeah. So people call a deep embedding when your combinators produce a description of something, meaning in terms of data constructors. It's actual data that you can now look at and evaluate and manipulate and introspect. Whereas a shallow embedding is not that. It's when you your combinators directly work with the stuff at hand. So shallow embeddings are more associated with functions manipulating stuff as the implementation of a combinator, whereas deep embedding is more associated with your combinators being just data constructors. Okay, so yeah, we would need a description. We would need a description, which is deep embedding, of our binary token parser if we wanted to try an approach like this with deserialization. Now, we don't have to just go for shallow or deep. We can actually mix the two. We can embed one inside the other. We can have a mixed deep, shallow. What does that mean in practice? That means data constructors that contain functions, where the functions are generated, specialized at the use site, and get embedded into a data constructor. So then your interpreter walks over the data structure and calls these functions at appropriate points. So that can give you some of the advantages of both. There are some things which are just slow to interpret, particularly just reading and writing little bits of memory. Those sorts of things are have a high interpreting overhead. So there's some things it makes sense to do in a shallow style, and others in a deep style. So we can do both, and we will do that here. So okay, here's a first go, and it's relatively simple. He says. Okay, it's a standard continuation monad. Is our decoder. On top, a continuation monad that produces a data structure. The data structure is this thing here called decode action. That's our actual concrete data constructor, which is the description. And you can see in the consume token case, it contains a function. And the decoder continuation monad is what we use to help us build that data structure. So that lets us write it in a nice, straightforward monadic style. But what it produces underneath is this data structure, this decode action data structure, which contains lots of functions. So the consume token primitive is a callback, a function. The interpreter will pass it the token that it's just read out of the input stream, and that function will return a new decode action, and the interpreter can go around again. Okay, so here is a little bit of what the interpreter looks like. It does exactly what I just said. For when we want to consume a token, we have to check where we've got enough space left. We'll decode the token out of the input stream, and if we did get one, we go around again. We call k. K is our continuation. We call k with the token that we got, and drop stuff off the input stream. So that's the sort of core of the fast path, if you like, of the interpreter, and that's nice because it's quite small, which is good. There are costs to this. Calling this continuation has a cost. As we'll see in a moment, allocating that continuation has a cost. But we're also allocating token constructors here. We're not allocating this result token string, result token byte fail stuff, but we are allocating, that gets statically eliminated, but we are allocating the individual token. Although that's relatively easy to eliminate. As we will see, it's the continuations that are more interesting. Okay, so the interpreter is relatively straightforward, and its costs are not too high, and this actually performs rather well. However, it's interesting to look at the allocations, because if you analyze the benchmarks for the existing binary and serial, you see that they do spend an awful lot of time doing GC. And if you play around with some of these things, if you try and reduce the amount of stuff they allocate, I found from playing around with earlier versions of this code that there was more or less a kind of linear relationship between the amount that they allocated in total and how fast they were. So here's some series of slides with some charts of what's going on with allocation in the existing binary and serial libraries. So this example here, this benchmark, is decoding quite a large structure. So we are ultimately getting into memory about half a gig of pointers and data constructors. And as you can see in this graph, the GC time is really dominant. It spends almost all of its time doing GC. Well, not almost all, about 60% or 70% or something. So it's a big factor. Now this graph is comparing the total amount of data that gets allocated during the run of this benchmark versus the amount that ends up in memory at the end. So the maximum residency, that's when the whole half gig or whatever has been deserialized into memory, versus the amount that's being allocated but it's just churning through data that's allocated but then collected by the garbage collector. So you can see in both binary and serial there's a massive amount of stuff that's allocated that gets garbage collected, that's not part of the final structure that's being allocated. And this seems like we ought to be able to do better. Right? We're allocating, we just saw that it spends most of its time in GC, and we're allocating vastly more than is strictly necessary to bring that data structure into memory. So well, we ought to be able to do better. Allocate less and go faster. A question over here?
How do you measure this?
How do I measure this? This is just from running the program with plus RTS-S. It just gives you the time it spent. It gives you the time it spent in GC, time it spent in the mutator, and the total amount of allocation and the maximum residency. That's all just on the command line from plus S, dash S, sorry, plus RTS dash S. This is the same decoding benchmark, but now instead of accumulating all that data in memory, we're deserializing it, but immediately throwing it away. So we're doing the same amount of mutator work. We're still doing all that decoding, but every time, because what we're doing here is deserializing like 100 records or something like that. So after we deserialize each record, we throw it away. So in some sense, we're doing the same amount of work, but as you can see in this graph, the amount of GC time is dramatically smaller, and so therefore the overall runtime is smaller. So again, this kind of gives us a hint that perhaps if we could reduce the amount of allocation, we could make it run a whole lot faster. In some sense, this deserializing is really bad for the GC because you're gradually growing a bigger and bigger structure as you deserialize, and the GC is going to have to traverse that probably several times. And the more that you allocate while you're doing it, the more times it's going to have to traverse that entire structure. So that was my intuition, we should get pretty good improvements by doing less allocation overall, because we'll simply have to traverse that structure, the persistent structure that just gets bigger and bigger and doesn't get garbage collected. We will have to traverse that many fewer times if we simply allocate less often and run GC less often. So I started pursuing this approach of, at all costs, let's eliminate all the allocations. And I'll try and share some of those techniques with you. Okay, so here, this is some success from that. I'll go into detail about how it works, but here's the sort of headline result. New continuation-based and new stack-based, two different implementations here of the decoder. Same graph as before of this one, the total allocation and the maximum residency. So we see with the two new implementations, the amount of allocation we're doing is dramatically less, and the maximum residency is slightly less. So we can radically reduce the amount of allocation we're doing. And what's better, it runs faster. So we've slightly reduced the mutator time, but we've significantly reduced the GC time. So this is pretty good. It's running about 2 and a bit times faster. It's not as good as I'd like, but it's not bad. Interestingly, sort of slightly spoiling my headline result, is that the stack one, which is what I'm particularly pleased with because it's so sort of interesting and complicated, the stack one allocates much less than the continuation-based one, which I showed you the code of a second ago. Well, I'll go into more details in the stack one. So it allocates a lot less, but unfortunately, in the time benchmark here, that doesn't make it take less GC time. It takes the same or slightly more GC time, despite the fact that it's doing much less allocation. And I don't yet really understand this. I'd like to understand it.
Does it hold on to data for longer?
Does it hold on to data for longer? I don't know. Shouldn't do. It's just maintaining a parse stack, basically. And those are all things that will be needed later on. It requires further investigation. I don't know. That's slightly disappointing, but it is fast. Anyway, as a slight side note, with this deep embedding approach, you get much, much smaller object files. This is an example. This is for a very large module with lots and lots and lots of types. Again, this is Cabal, in fact. Cabal package descriptions. The amount of code for derived read show versus ASOM's template Haskell version, binary, and then these two new implementations. And the object code is much, much, much smaller, which is nice. Okay, now my fanatical pursuit of fewer allocations. Okay, and here's another hopefully reusable lesson. Where should we look for allocations? And how do we check if we're doing well or badly, apart from looking at the final result and saying the total number of allocations are fewer? How can we look at the code and see that we're doing allocations or fewer allocations? How can we look at code like this and spot that this is being allocated and that's not being allocated? With my years of knowing how GHC works, I know that this will be allocated and that won't. But it's much better to go and look, to have something definitive to go and find out. So let's find out. So the best thing to do here is STG code, not core, but STG. STG is a special stylized low-level form of core that's the final stage of GHC's optimizer before it goes down to CMM. And it's stylized in such a way that all allocations are explicit. And that's how we can find out. We can go and look at that stuff and see, is it allocating, and what's it allocating and where? Is it allocating stuff we expect or stuff we don't expect? So to get that output, you want to use compile your module, and then you say dump STG, and this desuppress all reduces the amount of clutter. We don't need types. There's all sorts of things we don't need in this case. We just need to see let. In fact, let is what we're looking for. So in STG, every allocation is either a let or just a simple constructor application. It's unfortunately not quite as consistent as it always being a let, but it is always at least a constructor. You just search for the name of the constructor. Search for let, but yeah, it can also occur without a let with just the constructor name it's in. And conversely, all lets, at least those of a boxed type, not those of an unboxed type, are also an allocation. So what does a constructor allocation look like in STG? It looks like this. Let. STG is very low level. It's got lots of curly braces and semicolons, and slightly funny syntax. This token word, that is the name of the constructor, but the bang is just part of STG syntax, and that means it's allocating one of those right here, right now. And the square brackets, again, that's part of the STG syntax. That's not because we're using a list here. That is the arguments that are being packed into that constructor. So that is allocating a TK word containing an X, which is a word, an unboxed word, in fact. So that's what a constructor allocation looks like in STG. So you can search for lets, and if you see ones that look like this, you can see, well, that's what it's doing. That's a constructor. Closures as well, they also get allocated, and they look a little bit more funny. Their syntax is this lambda r. The r is not a variable, that's just part of the syntax. I do not know what it means. And I can't remember what SRT stands for either. Table, I can't remember. So what this is saying, this is a continuation k, which is a function. Really, this is lambda x. The square brackets x here, that is the argument to the function. And then, so we are allocating a function here that takes an x as an argument. And why are we allocating it? Well, we're allocating it for some reason. But why does it have to allocate these functions? Why aren't they just floated to the top level? It's because they are capturing some variable that's available in the environment. And that's why it has to allocate it, because the value of that variable is only known at that location. So here we are, in this particular example, we're allocating a closure k, a lambda x, something, 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 and we're passing that k, well, we're packing that k into the field of a consume token data constructor. So that there actually, consume token, is also an allocation, that's an example of where it's just being called as if it were a function. It's not using the let bang syntax, but it's also an allocation of that constructor. So, okay, that's what those continuations look like. And again, you can search for them because you can search for let and see if you expected those continuations or not. Okay, so let's eliminate the easy ones. I said earlier that we were allocating these term tokens. If we just specialize this a few times for the common cases and just pass an unboxed word instead, or an unboxed int, or an unboxed float, double, etc., we can cover all of those cases. There's only a finite number of the primitives, and then things like string, integer are boxed anyway, so it doesn't matter. Okay, so that's relatively straightforward. You just add more special cases and extend the interpreter, and there you go. That eliminates a few allocations. The closure ones are more tricky and more interesting. So if you have code that looks like this at the top here, decode and standard monadic syntax, this is our continuation monad from earlier that produces this deep embedding. So consume token is something that unfolds to the use of the consume token data constructor. Then what will the STG here look like? It involves allocating to closures. And why is that? It's because T1 and T2 are free variables in functions that have to be packed into data constructors. And so those functions have to be allocated because they capture these free variables, because they are closures. So because consume token, so if you look at the bottom one, say, we've got clause 1, and clause 1 is being passed as the argument to the final consume token. We're stuffing here a function into a data constructor, and that function captures variables in the local scope. So that function has to be allocated here so that it can be passed to the consume token. So that means basically in this style, a continuation monad that produces a deep embedding, in this style, every bind basically is going to be a closure because everything afterwards is going to use that value, probably. Yeah, I suppose if you consumed it immediately, maybe it wouldn't be free later on, but most of the time it's going to be, you're going to get, every single one of these basically will turn into a closure allocation. So that's quite a lot of closure allocations. The interpreter is constantly going to be switching back and forth between running a little bit of code that allocates the next closure, which goes back to the interpreter, and then that allocates another. Every single one is going to be an allocation. And that's dissatisfying. I want to do better. So, yeah, I've sort of said this already. This particularly comes up with continuations, because the continuation is the last thing you call, therefore the continuation is always a free variable, and therefore it's always a closure that has to be allocated, is the basic story here. And you can see that if you go and look at the STG code. You'll see that there's a K continuation being passed in at the top, and it's being used somewhere down at the bottom. Therefore, all the things in the middle have had to be allocated because they capture that K. So we will get lots and lots of closures this way. So, can we do anything about it? Well, I don't know of any general technique. It depends on the area. But in this particular case, yes! Yes, we can. We can use a stack. So, instead of writing the left-hand side, do bind, 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 and then use the variables that we bound earlier, we'll use a stack. And we'll say, push the thing onto the stack, and then push that thing onto the stack. And then locally, modify, alter the top of, alter the stack. And that stack altering function is now closed. It doesn't capture anything from its environment. It's a local lambda function. That function could be defined at the top level. It doesn't capture anything from its environment, therefore it doesn't have to be allocated. Hurrah! So that idea holds some promise. And then that means, of course, that the interpreter has to do more work, because the interpreter has to manage this stack. But just using a stack isn't enough here. We also need to deal with this continuation argument, if we're using this continuation style. And in fact, we'll have to abandon it, because there's nothing we can do. If all of our functions are instances are in this style of decoder, which is this continuation monad, then basically every single one of our compiled decode functions is going to be of the form lambda k, blah, 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 k, and so it's always going to be capturing k, and always going to be allocating closures to just because of k. So if we want to get rid of that, we have to abandon this this continuation style. We have to, as I said earlier, the functions must be closed, so that they could be written at top level, and then they won't have to be allocated. So, yeah, that means we have to stop using this continuation approach, which means we've got to do something else to sequence our stuff. So we can use a deep embedding of sequencing, which is not the sort of thing people normally advise. People, especially since it doesn't enforce anything. People like to say, well, if you do it, the shallow way, you guarantee your monad laws and stuff. If you do it, the deep way, you can't guarantee it. But we're going to do it anyway. So we're going to have a deep embedding of sequencing with a unit done and a sequence. Do the first thing, and then do the second thing. And this approach, in fact, does allow a fully static description of stack programs. I'll go into slightly more details about how this is going to work. There's sort of some question marks about the types here. But we're going to end up with code that looks like this. Or we do, in fact, when we do it right, end up with code that looks like this. This is the core, or STG, more or less the same at this stage. The core that you get from compiling some little program or fragment of the program. All of these things are top-level, statically allocated constructors, which refer to other top-level values. So let's see at the top, we've got D1 is push token, followed by D2. Yes, I didn't mention that I'm going to chain them. Each one, most of the time, these sequences are linear. I'd rather not have to use sequence everywhere. I'd prefer to chain because it's fewer indirections. So I'll come back to that point in a minute if I have time. So we can end up with code that looks like this. D1, push token D2, and it does some sequencing of doing something else, followed by D3, etc. So this is perfect, basically. There's no allocation while traversing it. It's all static allocated, and we can still have recursion loops here. So that's really nice. Let me see what time. What's my time budget? When did we start? Maybe you should just tell me to shut up at some point.
10 minutes.
10 minutes. All right. Cheers. Okay. If we follow the stack approach, we have to do more funky things with types to keep track of using the stack properly. Because our stack is necessarily heterogeneous, right? You can push, a thing of type A and then push a thing of type B, and we have to keep track of, and you can do that differently in every single place you write it. So we have to keep track of what's on the stack and the types of the things on the stack. So, for example, push token is going to go from stack S to stack token on top of S. So let's model that. We will say push token is a decoder. Now decoder is going to take two type arguments, the initial stack type and the final stack type. So it goes from a stack of anything, S, to token on top of, pushed onto the top of the stack, using this little data type, for just used at the type level to keep track of things. So now composition has this type, decoder A to B and a B to C, stick them together, and we have an A to C. So this actually fits the category class from the base package, identity and composition, and this one that we were going to use is actually flip of the composition. So this is, well, if you're familiar with it at all, you can think of it as a category, but another nice way to look at it is a type-indexed monoid, because this has a nice connection with type-indexed monads, which we will also be using in a moment. Type-indexed because we've got these two extra type parameters to keep track of, in our case, the type of the stack. There's other things in obviously that are instances of category where it's keeping track of other things. So our decoder, at least the bit that's describing the deep embedding sequencing, will look like this. Done is S to S, doesn't modify the stack at all, and sequence, the type I said earlier. Now, as I said a moment ago, for sort of primitive, most of the time it's just linear sequences of operations. Push this, go to the stack, push this, and without branching and sort of, rather than like call return, which is really what we want to use sequence for. So we make all of our constructors, like the primitives, push token here, contain the following chain of stack actions. That's the way we want to do it for performance, so that we can interpret it quicker. We can just walk down that chain rather than constantly bouncing back and forth with sequence. But unfortunately, that doesn't quite match our sequence operator type. We can make it match our sequence operator type by composing it with done, so making it follow with done. But now we don't get the chaining we wanted. But we can make it work because we can rewrite it locally using rewrite rules, and this actually works reasonably nicely. So we can pretty much always, so given those rules and written, question here.
Is it safe if rules are turned off?
Yeah, totally safe. Yeah, it just will produce more constructors that the interpreter has to walk over. It's just shortening chains, basically. That's all it's doing. So given if you write something like this, push token followed by something else, the rewrite rules will eliminate those dones and sequences and turn that into just a nice simple linear chain. And that's just faster for the interpreter to walk over. That's the only reason we do it. Speed. So you might say, oh, this is a bit ugly, all these rules and going between sequence and done and chaining style. But I want to argue that actually it's quite nice. There's kind of two approaches here. One is that you write, I know, your D-list style, where it has to be perfectly inlined everywhere to work and specialized, and you can't let well, in particular, if you're using the D-list, you can't let the continuation escape, otherwise it would have to be bounded, and if you abstract over that, it all goes wrong. So they're slightly, these are slightly fragile approaches. Whereas the do something sort of stupid and obvious and optimize it locally, I'm thinking it's quite a nice approach now, having tried both. In particular, I had one approach earlier where I was trying to limit the scope of these continuations, and then somewhere you wanted to abstract over something because it was polymorphic, some instance somewhere was polymorphic, and suddenly the whole thing just was terrible. Whereas this kind of obviously okay, but then improve it locally approach seems quite nice. Okay, so now we've done this deep embedding for doing things like pushing input tokens onto the stack. Now at some point we need to alter the stack, right? We have to have these functions that we write that change the stack. Now we're going to do this with a shallow embedding, i.e. functions that just actually modify the stack, because these functions are going to be very low level and they need to be fast. They're going to be literally things like read from here and write to there. And so that kind of operation will have a very high interpreting overhead. So we're gonna use a direct shallow encoding, just directly modify the stack for this part. So we're going to use a type indexed monad stack eval. So again, we've got these two type parameters, st stack and stack prime, the type of the stack before and the type of the stack afterwards. So it's exactly the same as we had a moment ago, but there's now an extra argument, which is the result, and that's why it's a monad and not a monoid. But it's still type indexed to keep track of the type of the stack. Now, the operations we allow here is that you can pop things and you can return a result. And then the way we use that is that the result that is finally returned is pushed back onto the stack. And that means that we can guarantee that a stack eval action never grows the stack. The most it can do is pop. It can pop some things and push a result. Well, okay, it can grow the stack by most one. And that means we don't need to do any overflow checks. Or the overflow checks can all be done in the interpreter, and none of the overflow checks need to be done in the shallow embedding code here, which is nice. That keeps the amount of code there to a minimum, and slightly faster as well. So the final code then looks like this: push, push, and then alter. Now, the body of the alter here is this type indexed monad, which is just the limited operations of popping things off the stack and returning some kind of result. And note that it is actually a stack. I got this wrong several times. You have to pop them off in reverse order. I got that wrong so many times. So yeah, this is an indexed monad. Unfortunately, while category, the type index monoid, is in the base library, there isn't one for monad. There's one of Edwards packages, which has got, well, there's dozens of these things, but none of them are in base. So I'm not using any of them because I don't want to. Binary is supposed to be kind of quite low down the package stack, you know. So we just use kind of classic style here. And there's no syntactic support, but it's not too bad. Anyone who is familiar with monads would understand this code. So, yeah, head back to the headlines. Does it work? Yeah. Unfortunately, it's not actually faster than the continuation one, which is kind of disappointing. I think there might be more performance to be squeezed out of this stack approach. There's more specializing that can be done. But I think really it requires now to work out why either of them are still slow or how they can be made faster. It requires, I don't know, Valgrind or Linux perf or something to figure out where is the remaining cost. Otherwise, you're sort of just poking in the dark. It's a bit fiddly. But still, it's a good result. We've got two implementations that are dramatically faster than the existing binary serial, both over twice as fast. Yeah, as I said earlier, the stack version allocates considerably less, but this doesn't seem to translate into actually spending less time in the garbage collector, and I don't know why that is yet. So I'm hopeful that the stack approach can be pushed even further, but if not, we'll just use the continuation one. Whatever's faster. So, what are the takeaway lessons here? Apart from that, this library is going to be awesome. So I think the big thing is that deep embeddings, you don't have to be. You should be skeptical about deep embeddings, but you don't, because they do involve extra allocation costs. But when done judiciously and with a very fast interpreter, they can be a reasonable approach. They can be okay for performance, and in fact, they can be excellent in some cases. I think it's easier to get more predictable performance with this style because of the not having to do this staged programming stuff. And perhaps that also, because of that, perhaps it's also easier, just in amount of, if you've got a limited time budget, it's perhaps easier to achieve reasonable performance. You might be able to achieve better performance by getting the perfect shallow encoding, shallow embedding, but perhaps it's easier to get reasonable performance this way. You certainly get much smaller object code size, which can be important. And the other thing, allocations can be important. And we can track them down by looking at the STG code. As I said, the final difference between the continuation one and the stack one, although it didn't turn out to be huge, but there was still a massive difference in the amount of allocation both were doing compared to the original. And I think that is very significant. So allocation can be important, and we can do something about it. So those, I think, are the transferable lessons. There's lots and lots of little interesting details which I didn't have time to shove into slides. I've got dozens more slides about lots of types and low-level trickery and hackery, and I better stop there, and people can quiz me afterwards about that stuff. Question in here.
Yes, so I wanted to ask that, do you have some baseline for the real-world benchmarks? I mean, that Facebook, Thrift, and Google also has something, Protobuf.
So I don't have comparisons with like Thrift and Protobufs and whatnot. I think those particular ones I think are not the right comparisons, because I want to make comparisons with things where you can just derive generic and then derive some type class and for free get serialization of Haskell values to something. Maybe if you've got a Protobuf compiler or whatever. But Protobuf doesn't really work well for big Haskell tree structures.
No, I mean C. So I mean some baseline. That what is our target? Is the end product 2 times slower or 10 times slower to what is achievable with today's C?
Right. So comparisons with C. No, I don't have a benchmark against C. That would certainly be interesting. You've got to make sure it's a fair comparison because you've got to turn it into structures, not just deserialize into a generic structure or something.
Yeah, so to C structs,
yeah.
Right?
So yeah, that would be good. I don't have such a benchmark. No. Other questions? Don't all speak at once. You had loads of questions earlier while we were going through the slides. All right. Well, in that case, I shall stop.
Well, just
Oh.
one comment. Brian O'Sullivan is now working on
Yes.
a direct encoding feature for a JSON. So instead of going via the value type like we do now, you go directly to a builder. And he asked me to review the code. So, but I think he's using like you said, like the easy approach of directly going to a builder.
Yeah.
And I think going via this intermediate structure, this stream of instructions basically, that would even speed it up more.
Yeah, so for the encoding side, taking a value and serializing out to JSON, that's kind of the easy way. That's the easy side of things. And you certainly could go straight to text from that. Going probably via an intermediate token stream would make a lot of sense. Yeah, that would be fairly easy. The hard one is the other way, is the deserializing, parsing the JSON, because fields can occur in any order. In binary, we have the luxury of knowing exactly what order things arrive in. But with JSON, you might have to get to the end of the file before you get the first field that you're looking for. There might be cunning ways of dealing with that, but you have to be quite cunning. I've not thought of them yet. Good luck.
It would be really nice to see a bit of competition between binary and ASL.
Oh, we'll always be faster than ASL. Come on.
Yeah.
if not, we'll have to eat our hats or something. Any other questions?
Duncan?
Yeah.
What is your take on the trade-off between code size and performance?
Between code size and performance. I don't know. I think you have to look at benchmarks to see. I mean, so there's this idea that if you're generating huge amounts of specialized code in all the use sites, that you're blowing your instruction cache and your branch prediction and all that stuff, and that may well be true, but it's hard to know for sure unless you do some proper low-level, perf, Linux perf or whatever profiling to find out.
Because I think
It's a reasonable intuition.
there's a new trade-off coming into space because if you want to use GCJS or related tools, actually build code which is deployed over the web, code size start to really matter much more than useful.
Right, yeah, so the comment there was that code size will matter more and more when people are doing things like using GCJS, where you're compiling to JSON code and deploying it over the web. People don't want to download multi-megabyte JS files. Code size does matter. So yeah, the interpreter approach would be rather nice there. Yeah. Another question?
One more question is, so you showed how each bind is basically allocated as one closure.
Yeah, each
So-
bind allocates a closure, basically, yes.
So my question would be here, could we, in this case, could we not exploit some extra benefits of using, for example, writing our parser as an applicative instead of a monad, so that you as the binary library can inspect the structure ahead of time and thus do similar optimizations as you did here?
So you would need, okay, so the question was, could you do something clever by using applicative to reduce the number of closures that you're producing?
So basically, the person who writes the get parser gives up the ability to inspect something inline, but as a result, you get more ability to analyze it ahead of time.
So you would need to use some sort of rule rewriting or something to, at compile time, translate into, because ultimately you have to produce data constructors. You've got to produce these consume token whatever constructors. It's all about what deep embedded, what value deep embedding do you actually end up with, what constructors do you end up with, and what are the functions embedded in those. Maybe there's some. I can't think of anything.
I found it very, very hard to get results from that.
I can't think of anything at the moment that would let you, because I don't think there is, because each consume token does give you a value, and it has to produce another closure which produces another thing, and you can't get away with not producing one of these consume token constructors. It has to be there, and it produces a value that you need to consume.
Look at your code. Essentially, what you're doing is lift applicative n function to then multiple decoders, which are completely independent. So if you have a token decode action which says lift this pay rate function for each pay, then actually you can translate this. By the way, I'm going to decode 3 independent streams, and only at the very end, the results you have, apply them. So then you can push it to the interpreter.
Right. Okay. So the only way you can do it is by changing the deep embedding. if you have an additional specialized, so perhaps you can, if you have a specialized constructor or constructors for that you might be able to use within implicative, then the interpreter can do something different with it. I don't know, it's perhaps worth exploring. Because certainly we would want to be using implicative here most of the time. And if there's something that would reduce the number of closures, that might make that continuation style a little bit faster than it is. All right, I think we're probably done and out of time. Thank you very much.